All right, welcome everyone. Today, we're going to be chemical detectives. We're diving into a really cool mystery, and our main tool for cracking the case is something called Fajan's rules. You ready? Let's get into it.
So here's the big question that's been bugging chemists for ages. We learn all these rules about how ionic compounds are supposed to work, but then some of them just don't play along. They act kind of weird. Our mission today is to figure out exactly what's going on.
Okay, let's look at our first clue. Over here, we have plain old table salt, sodium chloride. It's a textbook ionic compound, and it melts at a super high 801 degrees Celsius. Makes sense. But then you look at aluminum chloride. Chemically, it seems pretty similar, right? But get this, its melting point is only 190 degrees. That's a huge difference. How can that be?
To solve this mystery, we need to bring in our main suspect, and its name is polarization. This is the secret interaction that happens when ions get up close and personal, and believe me, it changes absolutely everything.
So what in the world is polarization? Well, in simple terms, it's when a positive ion, we call that the cation, gets near a negative ion, the anion. The positive charge of the cation starts pulling on the anion's fuzzy cloud of electrons, and it actually pulls the whole cloud out of shape. It literally distorts it.
Let's make this even simpler with an analogy. I want you to picture the cation, our little positive ion, as a small but really, really powerful magnet. It has this intense, concentrated pulling force.
And now, picture the anion, our negative ion. It isn't a hard little ball, it's more like a big, soft, fluffy cloud of electrons just kind of floating there.
So what happens when you bring that powerful little magnet close to that big, fluffy cloud? Exactly. The magnet's pull reaches out and warps the cloud, stretching it and pulling it out of its nice, round shape. That is polarization. And what it does is it makes that ionic bond start to share electrons, making it act a little bit like a covalent bond.
Okay, now that we know what we're looking for, let's find our first big clue. And it all comes down to the charge on the ions. Turns out, the stronger the charge, the bigger the effect.
Just look at the evidence laid out right here. Sodium has a +1 charge, and its chloride melts at a toasty 801 degrees. Magnesium has a +2 charge, and you can see the melting point already drops. But then look at aluminum with a powerful +3 charge. The melting point absolutely plummets all the way down to 190. More charge equals a stronger magnetic pull, which means more distortion and a lot more covalent-like behavior.
And hey, this isn't a one-time thing. Check this out. It's the same metal, iron, just with two different charges. The iron with a +2 charge has a melting point of 670 degrees, but bump that up to a +3 charge, and that one extra bit of positive pull is enough to slash the melting point in half. It's a clear pattern.
All right, we've got charge down. But for our next clue, we need to talk about size. Because it's not just how powerful the magnet is, the physical size of both ions plays a huge role in this whole mystery. First up, the cation, our magnet. Think about it. A smaller cation packs all of its positive charge into a much tinier space. That makes its magnetic field way more intense and focused. So a teeny tiny cation, like beryllium, is way better at distorting an anion than a big one like barium. And you can see the result, a much, much lower melting point.
Now, let's flip it and look at the anion, our fluffy cloud. The bigger that cloud is, the farther its outer electrons are from the center. They're held on more loosely, kind of like a dog on a really long leash. This makes them super easy for a cation to pull out of shape. That's why the giant iodide ion gets polarized so easily, giving its compound a way lower melting point compared to one with the tiny fluoride ion, which holds its electrons in a death grip.
So we've got our clues. It's all about charge and size. We know what causes polarization. Now let's put it all together and see what this actually does to these compounds. This is where we see the real-world results. Case solved.
So here it is, the big reveal. When you have a lot of polarization, it makes an ionic compound start acting more and more like a covalent one, and that leads to a whole cascade of changes. We're talking lower melting points, for sure, but also they don't dissolve as well in water. They can actually become colored, and they're even less stable when you heat them up.
Let's look at a super obvious example, color. Silver chloride is white because the chloride ion is pretty small and doesn't get distorted much. But silver iodide? It's a deep yellow. And the reason is that giant iodide ion.
It gets so easily polarized that it actually changes how the whole compound absorbs light, making it appear yellow to our eyes. Pretty cool, right?
And it's the exact same logic for dissolving in water. Silver fluoride has very little polarization. It acts like a true ionic compound, so it dissolves in water no problem. But silver iodide, with all that polarization making it act covalent, suddenly behaves more like oil. And what does oil not do? It doesn't mix with water. So silver iodide is insoluble.
Okay, one last thing before we wrap up, and this is super important. There are two words that sound almost identical and are so easy to mix up: polarity and polarization. We got to make sure we know the difference.
Here's the simplest way to think about it. Polarity starts with a covalent bond, a sharing bond, and makes it a little bit ionic. Polarization does the exact opposite. It starts with an ionic bond, and by distorting that electron cloud, it makes it a little bit covalent. They're basically two sides of the very same coin, just starting from opposite ends.
And that really brings us to the final big idea here. What Fajan's rules really teach us is that this line we draw in textbooks between ionic and covalent bonds, it's not a solid wall. It's really more of a sliding scale, a spectrum. And polarization is the force that can pull a compound from one side of that scale over to the other, proving that in chemistry, things are almost never black and white.